Okay, so this is the continuation of our topic one for part two. So last we stopped is at reflection. Okay, so we just finished this. This is from our previous slide, and then we stop at reflection. So reflection is just basically the redirectional of light. So basically, there's two type of reflection. One is specular reflection, another is diffusion reflection. So what we have generally practically for all the surface will be diffuse reflection, meaning when we shine a light onto a surface, due to the surface being very rough, so they will have different redirection of the lighting. So where we can find the specular reflection is on surface which is very very smooth, like our mirror or our PC screen, or even on the phone. So this is where you can see a bit of your reflection. Then you have a specular reflection due to the very smooth surface. But usually, in most of the case, you'll find diffuse reflection all around us. So our wall is what we have for our diffuse reflection. If the wall is very smooth, then you have specular reflection, meaning you can see your reflection from it. And then if you shine a light towards it, you will be able to get a very concentrated redirection of the light. So the light don't go anywhere. This is the difference between specular reflection and diffuse reflection. So when it comes to consideration of reflection in the calculation of lighting, we will be using back our inverse square formula, which you can see here, which is E equals to I over D square. So this is still the same as the formula here. So the new stuff regarding this is adding a reflectance factor into the equation. So depending on the surface, if the surface has a very good reflection, then you'll be near 1, meaning there's no losses in light. But if the surface have a very bad reflectance, let's say, for example, a quarry tiles, that means a lot of light strength or energy is lost during the reflection. So if you put this ratio into the formula 0.1, that means only 10% of the light energy is obtained after after reflecting off this surface. So when it comes to example of calculation in this example 4, we are given a point of source of light. So this point of source of light is actually hanging away from the ceiling. So when we have a point of light which is hanging away from the ceiling, and if it's exposed, then you will actually get a direct and indirect component, meaning you have a direct light straight from the point of light to the surface that you want, and then you also have a reflected component where the light is reflected off the center of the source of light towards the ceiling, and they bounce towards the table or the surface of the work area you want. So you're given this value, which is 1008 candela, and then you are actually given the scenario where this source of light is set 3 meters away from your floor, but also 1 meters below the ceiling. So here, from your point of source of light to the ceiling, is actually a 1 meter distance, and then from your source of light to the floor is actually 3 meters. So in total, you have 4 meters of ceiling from floor to the ceiling. And then you're given a reflectance ratio of 0.5 for your ceiling. So this means that your ceiling is able to reflect 50% of the light energy back. Okay, so you will need to calculate what is the direct and reflected component for this question. So given the value, the illuminance is 1008 and then the distance is 3. For the direct component, you just use the inverse square law, which is this, and you submit in, you get 200 lux. So for the reflected component, you know that you're given that the reflectance is 0.5. So you using back the same formula, you have to multiply it with reflectance, which is 0.5, only 50%. But do bear in mind regarding the distance. So instead of the light point directly reaching the floor or the floor beneath the light, for the reflected component, it's actually mentioned that this light is 1 meter away from the ceiling. So from here, to take into account for the reflected component, the light needs to actually travel from here to here for 1 meter, and then after it's reflected from the ceiling, then they'll have to travel another 4 meter, which is from here to here 1 meter, and then from the light to the floor, they actually need to travel 4 meter. So that's where this distance come from. So they need to travel 1 meter from the source point to the ceiling, and then 4 meters down to the floor. That's where you get the distance of the light that needs to be traveled to the floor beneath the light, which is 5 meter. So you put it all into this formula, and you get that the reflected component based off this setup is 36 lux. So this is how you can make use of the formula, and then based on how the lighting is set up, if there's reflected component or uh, non-reflected component or the direct component, and how it affect the illumination of the area. So in this case, the lux or illuminance in this floor is actually 236. You have to add this direct component and reflected component together, and you get the total illuminance on the floor beneath the light. But since this example 4 just mentioned to calculate the direct and reflected component, if you just leave the answer like this, it'll be good enough. So when it comes to doing calculation question, you have to be careful on what is mentioned by the what's given and what's asked. Okay, so since this question just mentioned like to calculate the direct and reflected component, just doing it and leaving it like this is good enough. Okay, so next one, we have glare. So glare is basically just excessive amount of brightness in our field of vision. So there's actually two types of glare. So we have disability glare and discomfort glare. So disability glare is basically very bright light that cause you to not be able to see the detail or see properly. But for discomfort, it's basically just visual discomfort, meaning you can still see the detail. It doesn't necessarily mean you cannot see the detail. So it's not painful. But for disability glare, it can be painful. It can be up to the level of pain that you cannot see the detail and you do not want to see it. So this is the difference between different type of glare. So you can encounter a lot of glare in our daily routine. So usually when it comes to glare, is usually from our natural sun. So our sun is actually very bright. If you're out on the road in a car, sometimes you'll see that at the edge of the car there will be a very bright glare. So that example is actually a disability glare. So you try to want to shield away our eye from this sort of glare because it's so bright that it's painful to our eye that we actually cannot see the detail besides it. So for discomfort glare, usually is on our artificial lighting because it's not so bright. We can look directly at it. So this way, although we can still see the detail beside it, it's not very comfortable for us, but it's still not at the level of pain where we cannot look at it. So this is a difference between the glare available, the two types of glare available. Okay, then we have our lamp. So the function of all this artificial lighting, there's actually three primary function. So why we want to have artificial lighting is because we want to be able to do our activity, and we want to be able to see and move about safely, and then finally we want to display something. So it can be a product that we want to sell, or it can be a building. So this is the function of why where there's a creation of lighting in our daily life. So the oldest source of light can come from a fire and a candle or a kerosene lamp. And then for modern source, we can have our incandescent lamp or the tungsten filament lamp. Either that, we have a fluorescent lamp, discharge lamp. So the not mentioned lamp here or the lighting here is the LED. So all of these types of lighting sources is actually just a means of providing lighting to us. But behind the function, behind the methods on how they are able to display or give us light, they have different mechanism behind it. So, for example, for this flame, is due to using up the material and burning it up to obtain flame. But this is not very efficient because we are actually generating a lot of heat. So light is just a byproduct of this method of lighting generation. So let's have a look at this. So for tungsten filament, so this is the first type of modern lighting. So so this is the first type of modern lighting available. So the method of how artificial lighting is produced by this sort of light is through passing electricity through a thin material. So once electricity is passed through this thin material, they actually have a resistance. So when you pass energy through a material, they have a resistance. They actually get very, very hot, and that is where the lightings come from. So it's not perfect, but it's a controlled fire lah, as opposed to just a flame where you light up stuff. So this is the first modern lighting available. So they have a few characteristic. So this is the most common light bulb. It's very simple to install, and it's actually quite cheap because of the simplicity of this product. But they have their downfall because of the way this lighting works, the mechanism behind it of using electricity to heat up the material in it. So they actually has a very low or shorter lifespan and lower efficiency. So not all the light or not all the electricity is used to properly light up or converted into lighting. So the wastage is on the heat energy still. Okay, so next we have our tungsten hologen lamp. So instead of using a material to get our light, we instead have halogen gas, which is iodine and bromine. So here, in this case, we actually still run electricity through it. And then when electricity is run through this lamp, they actually activate the gas inside it. So uh, this type of lighting generate light. So they actually have a longer lifespan when compared to this, because instead of heating up this material, there's actually a durability toward this. So once you burn it up or it's heated up for a very, very long period of time, it will actually lose its product. It will actually decay. But in this case, we are actually we are actually activating the gas. So it's actually higher efficiency as compared to the this general light, but it's still not the best. So we're actually still finding more and more ways to light up. Okay, next is we have a reflecting lamp. So this is just basically having a body or a way to redirect all the light instead of just letting it go everywhere. And then we have your low voltage. So this is basically still incandescent lights, but there's a bit of modification towards the material. So you want to have the filament shorter, thicker, and stronger. And then next we have what is now currently very commonly available all around us. So when it comes to commercial, you'll notice that you'll be able to see a lot of fluorescent lamp, which is this long tube. So you'll find a lot of it in a lot of commercial building. So the mechanism behind how they give us light is still through gas or vapor. So they are very similar to this tungsten hologen lamp. So electricity is passed through this gas and they are ionized. And when they ionize the gas, means they activate the gas actually produce the light. So here, some of them are using mercury, but they actually have a bit of higher cost as opposed to the production of this general lighting, but they give better illuminance. So not a lot of electric energy is lost through heat because they are only used to activate the gas, and the activation of gas is where the light comes from. Okay, so we have our compact fluorescent lamp. So it's just in a more compact method. It's form. It's in a more compact form. So here, this gives a general idea lah. For on this table, it just gives a very general idea on how efficient a light is as compared to the method in how they provide lighting to us, artificial lighting to us. So in a case of tungsten filament, where we use a material, we run through electricity through a material to heat it up at a very, very high temperature to produce the light. If you use an equivalent fluorescent lamp, it actually only costs about 9 watt as opposed to 40 watt. So this watt energy is the SI unit or the value to represent the number given on how much energy is needed to operate this light. So the higher it is, the does not necessarily mean the worse it is. It just means it takes more energy to run. So when it comes to efficiency or how good the light is at converting energy to lighting, we want to take note of the luminous efficiency. So meaning we want something or we want a light that actually does not eat so much energy, but is still able to produce the same amount of lighting as opposed to what our traditional lighting are able. So in this table, it's actually able to show that the tungsten filament light or the first light that bulb we have, if you were to compare it to our modern lighting, we can have up to a difference of 20% or 30% of difference of efficiency. Meaning our modern equivalent counterpart of lighting is actually so efficient that one of the olden days light bulb represent up to five lighting available. So this is what this table is trying to show you. So what is not mentioned here is actually LED lighting. So behind the mechanism of this LED, so uh, instead of having electricity heating up the material like our first general lighting service lamp, our incandescent lamp, or even using gas. So this is not in your exam lah because it's not in your slides. Just so for your extra knowledge. So how an LED works is there's they are actually using the most basic form of electricity, meaning they are using diode to generate the light. So at the most basic level, we have a semiconducting material. When we pass electricity towards this semiconducting material, which is a diode, we're actually forcing the electricity to jump from a point A to point B, from a positive node to a negative node. And then when that jump happens, that is where the light comes from. So that is the mechanism behind how LED is able to generate lighting. It's through a diode, and we are actually forcing the electricity to generate photon. So if you go back to what light is about, it's actually a form of energy, and it's weightless, and it's a photon. So why LED is so efficient is because we are making use of this generation of photon instead of instead of creating heat to generate the lighting, or we are ionizing the gas. So this is what makes LED so efficient in terms of generating lighting. But it's not in your slides lah, so you won't be tested on it. So in the future, maybe I can put it in, but then it will be more material for you guys to study, and when you're tested in the exam, it'll be more material for that. Okay, so if you were to compare LED against this fluorescent lamp, then it will be even more efficient as compared to this. So the efficiency is due to the way how different light generate their lightings. Okay, so hopefully that is clear. So we have two properties of a lamp. So higher voltage does not necessarily mean is a very good lighting appliances, but when it comes to selection of the right lamp, you want to find out the efficiency behind it. So the ability of a lamp to convert electric energy to light. So that's where we get our lumen per watt. So lumen is the amount of light emitted, and then you have your watt, which is the electric energy. So efficiency is basically lumen divided by watt. And then next you have your life, so a lifespan, a life cycle. So how long electric appliances can work? Each of them, by right, the manufacturer will have to put in a lifespan. So this is to allow the consumer to factor in the costing of the lighting. So when you have a large scale installation, let's say for example a commercial building for a shopping mall. So for a shopping mall, there's actually a lot of lighting that needs to be installed in the building. So you want to choose a light source which have a very long lifespan as opposed to a short lifespan. So why? Because if once the life of this lighting is over, there's a high chance that the light bulb will not turn on anymore. So you need to replace this light. So this is what it means by a lifespan of this lighting. So it doesn't just mean that the light will just turn off, but the efficiency of this lighting will also be affected as time passes by. The material in the lighting will actually degrade or decay with time. So when the material decay with time, then the lighting, the illuminance will also decrease. So it won't be so efficient in converting this light energy or this electric energy into light energy. So nominal lifespan or the life of the lighting will always be given by the manufacturer. So it's by law lah, that they need to provide this data sheet. Okay, so next we have our property of lamp. So here, this table show you different type of lamp types. So based on these lamp types, we have the different voltage range and how efficient it is, and then how long they last, and what is their color temperature, and where they are usually applied. So here there's a short note lah, that higher voltage lamp generally have higher efficiency and longer life. And then for value for efficiency and life of most discharge lamp are subject to improvement. So as we go year by year, there's actually R&D, research and development on lighting. So very big manufacturer like Philips, they will still continue to improve on their technology to give better value, better value lighting, and better efficiency and lifespan lighting. So they will always have a budget to improve upon their product. So why why do I say that? Because of competition lah. So they are not the only one of the big manufacturer of lighting out there. So every company are pouring in money to research and develop further, so as to not be obsolete, meaning as to not fall behind their competition. They will have to keep improving on their product, like what we have lah for our computers. So year by year, you see that product will always keep improving. There's always an improvement of it. Either we take notice of it or don't, but they will have to keep making improvement as to not lose out to the competitors. So if the competitors are able to make even better or cheaper product, then they will have to follow. Okay, so I think we can have a break